Previous video, we defined the power spectral density of a random process. It's indicated notationally this way, and what it is, by definition, it's the Fourier transform of the autocorrelation function of the process. It only applies to wide-sense stationary processes. If you were given the power spectral density, you could find the autocorrelation function. And a fallout is that the mean square value is this integral, one of these two integrals. Integral of the power spectral density. If it's in terms of radians per second, you got to divide by 2 pi. If it's in terms of hertz, frequency in hertz, then it's just the area under the curve. It's this total integral. So let me talk a little bit more about this relationship in this video. So the mean square value, there's like 3 different ways we could express the integral. Here in terms of radians per second, omega. Here in terms of frequency in hertz, where you don't have to divide by 2 pi, which means that the mean square value is the total area under the power spectral density curve, hertz. And we call that the power of the process. In hertz, power spectral density is going to be power per unit frequency. So if you integrate over all frequencies, you get the total power of the system, and that is the mean square value. We're going to be coming back to this guy a little bit later, I believe. Sometimes we'll set S equals J omega, and this, just by that substitution, this integral is the same as that one. We'll get to that a little bit later because sometimes it's easier to do it in these terms. But I don't think I need to go into these words. Let's do an example. Let's look at the words first. Somebody took measurements of a system and calculated that the RMS output voltage is 100 microvolts. And the frequency spectrum of that noise is just flat from 0 to 10 megahertz, 0 above that. So we're asked to find the power spectral density and the autocorrelation function. Okay. Power spectral density has to be metric. So even though it says it was measured from 0 to 10 megahertz, PSD is going to go from minus 10 megahertz up to plus 10. And it said it was flat between there. So the PSD is going to look like this. Let's see, these are in terms of hertz. Yeah, 0 to 10 megahertz. So this frequency units are hertz. And it's flat over that time, over that frequency, over those frequencies. But we don't know how high up it goes. But we know the RMS value. The RMS value squared is the mean square value, which is this integral. And that's just A times this total length. So it's twice this F max. This F max is going to be 10 times 10 to the 6, 10 megahertz. So we know the RMS value squared equals twice the height times that frequency. And we were given the RMS value. So plug in all those numbers and you get a value for the A, how high up this thing is. Amplitude. It's 5 times 10 to the minus 6 volts squared per hertz. So we have PSD, done part A. For part B, we've got to take an inverse Fourier transform. So we're going to need a table. And in the frequency domain, it was a sinc. Excuse me, in the frequency domain, it's a pulse. This is the frequency domain. It's a pulse in the frequency domain, which looks like this when you use unit steps. It's a unit step from a minus omega 0 to a plus omega 0. And in the Fourier table, these omegas are in radians per second. So we're going to have to do that conversion. But anyway, pulse in the frequency domain translates to a sinc in the time domain. So we have this, if I multiply by A omega 0 over pi on both sides here, I'll have A omega 0 over pi sinc equals this A times this part. And the omega 0 here, I got to convert to radians per second. So I'll multiply the Hertz by 2 pi. The rest of this is getting everything to square up so that terms match. The scaling and the parameters of the table match numbers of our problem. And there's a weighting to then calculate what the autocorrelation function. It's going to be some scaled version of sinc, where this omega 0 was 2 pi at F max, which was it 10 to the 7th Hertz. There's the omega 0, 2 pi 10 to the 7th, and we had the A from the previous chart. That's what that was. So now we have the autocorrelation function. Old square. Autocorrelation function will be in whatever your variable is, those units squared. Frequency spectrum will be in the units squared per Hertz. Right, that's a little bit, we'll say white noise for, I believe, another, we'll do that in another video. So that was, let's see, the power of a random process, which means that each square